This video is our first in circuits. This covers current and resistance. Now again, much of this information we covered last year, so it's just going to be a quick review. Now, we know that electrons are the ones that move. Protons don't actually move. But electrons move from low potential to high potential. Okay, that's something that we talked about when we were discussing potential. Okay, so they technically fall up, which is a bit awkward. So since this is backwards compared to mechanics, it is easier to pretend the positive charges are moving. If the positive charges were able to move, they would fall from high potential to low potential, just as mass falls from high height to a low height. So, since the charge on protons and electrons are exactly the same, it doesn't matter mathematically which charge is moving. Again, the only difference is the direction of the charge flow. So, the most important thing is that we're going to be pretending that our protons are moving rather than our electrons. Now again, we talked about the motion of charges, and this motion is caused by a potential difference. Now batteries and generators create a potential difference. This is the height that we're talking about. As they fall, they do work and run electrical devices, and we can actually calculate all of that. So if we accept that positive charges are moving, then charges move from the positive plate to the negative plate of the battery. So when a battery is connected to wires, an electric field surges through the wires from the positive to the negative terminals of the battery, and this takes place at the speed of light, as a field has no mass. The electric field creates a force on the charges, causing them to move, so theoretically they should accelerate to the speed of light. However, as the charges move, they start colliding with one another, and with imperfections in the wire. So these collisions slow the charges to a very slow speed in centimeters per second. So we can actually calculate this, which is current, the amount of charge passing through a point in a wire every second. Now, this is the rate that charges move through a circuit. So I is current, and this is our new unit, amperes, or amps, as we call them for short. Q is still going to represent charge in coulombs, and T is still time in seconds. So again, very basic information, conditions for a current to flow. We know that there must be a path made of conducting material. Another way to say this, we need a closed circuit. And we need a potential difference. So that means we need a battery or a generator that provides us with that potential difference. Generator. In this example, we have 20 coulombs of charge that move through past a point in a wire in 40 seconds. So we're asked to determine the current in the wire. So remember that I is equal to our charge over time. Again, 20 coulombs of charge have passed through in 40 seconds. So we have 0.5 amps. In part B, we're asked to determine the number of electrons moving through a point each second. Well, we just said that current was 0.5 amps, or 0.5 coulombs per second, 0.5 coulombs per second. Again, coulombs is a unit for charge. So, if you know that 0.5 coulombs, and we know that there are 1.6 times 10 to the negative 19 coulombs in one electron, then we have 3.125 times 10 to the 18 electrons. Now, all conductors have molecular imperfections that slow the current down. Now, these imperfections act like air resistance in mechanics. So, again, we know that resistance is variable R. It has units of ohms. So if we wanted to calculate the resistance in a circuit, we could actually use this equation, where rho is the resistivity of the material. Again, this is a measure of the quality of the material that it's made out of. L is the length of the wire, and A is the area of the wire. Again, wires are usually cylinders, so we're going to be using pi r squared as our area for most conditions. Now again, if we look at this equation, if rho goes up, then my resistance goes up. If length goes up, my resistance also goes up. If my area goes up, then my resistance actually goes down. And that makes sense because if you think of a highway, if we increase the area, then we are producing less traffic. So if you were to make the area actually smaller or narrower, it's like reducing the number of lanes on a freeway. Now, there's one factor that does affect resistance that we haven't mentioned in this equation, and that's temperature. Increasing temperature also increases the resistance, so that's an important piece that we need to remember. The charges now have to get past imperfections that are vibrating faster. In this example, we have a copper wire with a resistivity of 1.7 times 10 to the negative 8. So that information is our rho, 1.7 times 10 to the negative 8. And it has a length of 5 meters and a radius of 1.5 millimeters, or 0.0015 meters. And we're asked to determine the resistance of the wire. So we can just plug in all of the values that we have. Again, for our area, we're going to be using pi r squared, again, assuming it's a cylinder. Our rho is 1.7 times 10 to the negative 8. Goodness. Our length is 5 meters. And we have pi r squared. Okay. Again, I'm using a lot of parentheses so you can make sure not to make any errors in your calculator. So you should get a resistivity of 0.012 ohms. Resistance. Now, again, we know that we can use resistors or add resistance to a circuit. And resistors are specifically designed to create a known amount of resistance. Now, you may ask why we're adding resistance to a circuit anyway, essentially wasting energy. Well, components in electrical circuits are very sensitive and need an exact amount of current and potential to function correctly. So, with resistors with known values can be used to channel electricity down the correct path in a complex circuit, and they can be used to ensure that the electrical components are not overloaded. Again, all of this is just background information so that you understand where we're coming from with all this information. Like light bulbs are actually a specialized form of a resistor. We know that inside light bulbs, we have a thin wire known as a filament. So as this current goes through our wire, it's hitting a bunch of other particles or other charges and also other imperfections in the conducting material. So the more imperfections, the more collisions, and the more heat that is generated. Again, that relationship with the temperature. So filaments are made of a material that glows, giving off light when they get hot enough. Again, a light bulb is a resistor that glows. Now, one of our biggest equations in this entire unit of circuits is Ohm's law. Now, Ohm's law relates the potential of a circuit to its current and resistance in that circuit. Again, V is potential, I is current, in unit of amps, potential, unit of volts, resistance, unit of ohms. So, let's say we have a 3 ohm resistor and it's connected to a battery producing 6 volts. Okay, again, we see that ohm, so it's our R, our volts, so it's our V, and we're asked to determine the current. Well, that's simply V over R equals I, or 6 over 3 gives me 2 amps of current. Again, one of the very important concepts in this unit is also power. Now, power is the rate at which work is done. This is something that we saw in mechanics. Another way to say that is rate of change in energy. So we saw this equation before. This is power is equal to work over time. Power, which is in units of watts, is equal to work, which is in units of joules, over time, which is in unit of seconds. So again, a watt is a joule per second. Now in electricity, it will be electric potential energy that changes. So our change in electric potential energy over time is equal to power. But remember that delta U is equal to Q times delta V. So if I make that substitution here, I can see that I have Q over T here. And we just learned that Q over T is equal to current. So we can make another power equation, which is equal to P equals IV. Power is equal to current times potential. Again, power, which is in watts, equals current, amps, times potential, volts. Now, normally in problems, you're not going to see them flat out say, calculate the power. Instead, they're going to ask you to calculate other things, like the rate of work done, the rate that energy is used or consumed, or the rate that energy is produced or generated. Any of these three ways, they're telling you to calculate power. Now, putting it all together, we just learned that power is equal to I times V. But before that, we know that Ohm's law, which is V equals IR, also exists. So we can make another substitution. Where I see a V, I can put in I over R, which is Ohm's law. So this simplifies down to power is equal to I squared times R. But I can make another substitution. I can say that V over R is equal to I. So where I see an I instead, I can put in V over R. And that becomes V squared over R. So all these three equations are ways to calculate power. So again, when you are determining the information given, remember that there are different ways or different equations for power. In this last example, we have a 3 ohm resistor that is connected to a battery producing 6 volts. Again, we just talked about that V is equal to IR, and we have 6 volts and 3 ohm, which is our resistance. Okay, we had already calculated that our current was going to be 2 amps. So we're asked to determine the power of the circuit. So this can be done in 2 steps. You can say that power is equal to I times V. So we calculated I to be 2 earlier. So that's one step. And then we can use that information here. So 2 times R volts, which is 6. So we should get a power of 12 watts. Or, again, if you're familiar with all the other variations, I could have just done, without solving for current at all, that current is equal to V over R, which is V squared over R, which is 6 squared over 3. Again, just 12. So really, if you can remember one of the power variations and V equals IR, you can use any of your substitutions to kind of figure out another way without having to do more than one step. Again, you don't have to write this part down. You really should only be focusing on anything that's in any text that's in color. So don't write. I'm just going to talk about what happens inside of a battery and how we use that to calculate our voltage and our resistance in a circuit. So, batteries consist of plates that are charged by a chemical reaction taking place between the plates. The reaction provides the energy to lift charges from a low potential to a high potential. And the EMF, this is the part that we're going to focus on, created by the chemical reaction is a potential difference that drives the electrical devices attached to the battery. Like other sources of power, batteries are not 100% efficient. Since batteries are made of conducting material, they have resistance. And the resistance inside of a battery is called the internal resistance. This part you do need to write. The EMF of the battery is a theoretical potential that would have been reached if there were no resistance. The actual potential produced by a battery is less than the EMF due to the loss created by the internal resistance. The actual potential is called the terminal voltage. Now, again, everything in color is important. The terminal voltage is the potential difference between the terminals or the ends of a battery. This terminal voltage, which is V, is equal to the EMF produced by the battery minus the current in the battery times the internal resistance, lowercase r. Now, for the most part, when we have our internal resistance is negligible, which is the case in most problems, then our voltage will simply be equal to the voltage stated on the battery, or also known as EMF. Now here we have a graph of terminal voltage. The equation for terminal voltage is linear, as we can see in this equation. To determine the exact look of the graph, simply rearrange the equation to match the y equals mx plus b equation that you're more used to. So if you're asked to solve for the voltage versus current graph of a battery, again, anything versus anything means y versus x. So that means current is going to be on the x-axis. Again, we rearrange this equation so that it matches the mx plus b. And so we can see that our slope is going to be our negative r. I is on the x-axis. V is on the, what we see here, the graph, the y. And our EMF is our y-intercept. So again, this problem is pretty straightforward. A battery has an EMF of 6 volts. Again, that EMF is our little sigma symbol here. And an internal resistance of 0.10 ohms. Remember that ohms is a unit for resistance. And we're asked to determine the terminal voltage, which is V, if we have a current of 3 amps running through the battery. So we're given all of our information. We can simply plug it in, and we get a terminal voltage of 5.7 volts. Again, for the most part, internal resistance is going to be considered negligible unless you're otherwise told to include it into your equation. So when internal resistance is negligible, R is equal to 0. That means this piece is going to go away, and all you're left with is our terminal voltage will be equal to the EMF produced by the battery. So when working with batteries, Ohm's law and the power equations modify as follows. Again, you really don't have to make these modifications unless you already understand what's going on, but it's a good idea because you might see them in this form on your multiple choice questions. And lastly, we're going to start getting into the real circuits building problems next video. So it's important to already be familiar with the symbols that we're going to be seeing. So make sure that you copy all these down, and we'll go over them next time. Again, this is an ammeter, and this is a voltmeter. And finally, we're going to look at electric field and charge density. Now, we said if there's a potential difference at the ends of a conducting material, then there's also an electric field pointing from high to low potential. The electric field is proportional to the resistivity, which is our rho, and charge density, which is our J. So E, which is our electric field in the conductor, is equal to rho times J. And we've seen all of these variables before. Especially this J, we saw it in our 2 videos ago, where J is equal to the current per unit of area. So let's try an example. Here we're asked to determine the electric field strength needed to generate a 2 amp current in a copper wire with a resistivity of 1.7 times 10 to the negative 8 and with a diameter of 3 millimeters. Again, let's go ahead and just label all of our information. We have 2 currents, so that's 2 amps. Our resistivity, rho, is 1.7 times 10 to the negative 8. And then a diameter of 3 millimeters, or 0.003 meters. Again, that information is not entirely useful. It's actually better if we convert this to radius, which is 0.0015. Okay, and then again, with all of this information, we can actually pull out our area. which here we can assume if we're given diameter that this is pi r squared. Which gives me an area of about 7.06. I'm going to go ahead and use this whole number in my calculator, but right now I'm only going to write this piece. And then again, finally, you're asked to solve for the electric field. So you can use the equation we just were given, where your resistivity, which is 1.7, times 10 to the negative 8, times our current density. Again, remember, current density is current per unit of area, which we were given to be 2 amps over the number that we got here, 7.06 times 10 to the negative 6. And you should get a value of 0.0048 Newton per Coulomb.